Now that we have seen how the software is actually interacting with the hardware, what the software is expecting from the hardware, what is our ABI, now we can take a deeper look at the hardware's internals and build up this architecture. Uh, we will be talking about all of these modules in a higher level, like you can see here, all these modules. But what is more important is we will eventually use all these modules to come up with this architecture. And you can see here, for the sake of ease, we are also defining two distinct type of data. We either having a multi-bit data, which we call the data path, or we have a control signals. Now the data path is colored with purple, while the control signals are colored with blue. So control signals will have a single bit, but this single bit can change the whole state of the accelerator. If the command router tells the accelerator now it is the right time to run the given description, a lot of things can change. Each of these signals and data paths are actually written here, defined here for convenience. So for example, the commands are received by the CPU core. The response is the response we are sending back to the CPU. We have noted these here, and you can find almost all of these signals and data for each module we will talk about. Starting from the command router, you can see that we are receiving a command from the CPU, and we are responding to that specific command through the same module. Now, this command router will actually decode the command, and it will send appropriate signals that the accelerator can understand that are much more simpler. For example, we will set the description right now. Well, like we have stated earlier, we may have an attention, a causal attention, a matmul. All these details are in this description. We will set the description, we will run the description, we will reset the accelerator, we will clear the accelerator. We are busy now, we can't process any data. All these signals are handled by the command router. Coming to the data, we can see that the description address that the CPU have passed is also an output of the command router. It will actually be plugged into the Atik controller, this description address, so the Atik controller can figure out a way to ask the direct memory access to retrieve this descriptor and store it in its registers. The counter index is also a kind of input from the command, because we will ask for specific counters in the accelerators to retrieve, and the counter value is actually the accelerator's response to that counter index. So imagine we have a counter bank where we count how much time we have spent in accessing the memory, how much time we have spent in computation, how much time we spent in other things. The CPU might ask like how much time we have spent accessing the memory through that index, and we will retrieve that data. We will also retrieve the status word. The status word will tell us what status is the accelerator is at right now. It is okay. Is there anything bad happening? So coming to the next module, which is actually directly coming after the command router, we can see the Atik controller. The Atik controller will actually control the attention and MatmulControllers. You can see how here that Atik controller directly controls either the matmul or the attention, and it will actually be a huge part of our accelerator. You can see here that it receives the set description signal, the run signal, the reset signals. This is duplicated here. Let me just delete it. It will receive these signals, and depending on these signals that it is receiving from the command router, it will tell the matmul to start, or it will tell the attention to start. And after we have computed the matmul engine will tell us the matmul is done. And now we can start thinking about how this whole big state machine is actually shaping our our accelerator's behavior. You can see here that we are also passing the description start uh, signal. So the descriptor DMA here will go and figure out how to find that descriptor, that descriptor we have passed through the instruction. If it find it and everything is okay, it will say description done. Like we have stored the description, now it is in our registers, and the controller will say, okay, if I receive the run signal from the command router, now I can run either a matmul or a tension. We are passing a causality signal, which means that if we are doing a tension, if it is a causal or not. Also, now we are passing the descriptor itself as a whole data bits for the accelerator to consume, so it doesn't deal anymore with the description address. You can see that we are taking the description address as an input, and we are outputting the description itself with the description address, because at the first cycles we don't have the description itself, we have its address only. After we receive the description from the description reader, we start outputting the description itself. So coming to one of the most important controllers, which is the MatmulController, you can see that we are receiving two important signals, which is tile is active, tile read is active, and tile write is active. Now I'm about to explain what a tile mean and how are we handling the matmul operations. After that, you will understand what this tile read active and tile write active means. See how are we going to develop the matmul data path for our accelerator, and how it is going to be solving this matmul problem. How are we going to tile over these matrices and do the computation overall? First, we need to figure out a way to solve this by hand and see how the algorithm proceeds when you solve it on paper. So first, you can imagine that we have an A matrix and a B matrix with the defined shapes and dimensions. And basically, what we do is that the product between the row vector and the column vector of the second matrix to obtain the first element. When you write this more mathematically in a generic way, you can see that we are using the same inputs for different outputs. So A11 actually is involved in the computation of C11 and C12. B11 is involved in the computation of C11 and C21. Now, what this means is that we are using the same data over and over again, and we should not fetch the same data from the memory over and over again. We should reuse it. We should cache it and reuse it for further computation. And better, not just cache it, but pass it to the next element so it can use it without any memory overhead. The other thing that we should pay attention to is that we need a regular processing element. What I mean by the regular processing element, that it should be so simple, because what we are doing is so well defined. We either do multiplication and we do summation. So these are two basic operations that each small building block will support, and by attaching those small building blocks together, we should be able to solve this problem, because you can decompose it to these small building blocks. Furthermore, we need a scalable solution. We need a scalable hardware, because we are not going just to multiply two small matrices. We are going to multiply huge matrices, and the hardware need to support all these huge matrices. Furthermore, I mean by scalability, not just scaling the problem, but also scaling the hardware itself. I need a knob that by increasing it, I can increase hardware's overall throughput and performance. And now we will see how are we going to implement this. So imagine we have a cell right here. This cell is responsible for basic multiply accumulation. So it will multiply two inputs and accumulate what it has from before. So if I need a mesh that contains 4 cells 2 by 2, I need to specify and say that these cells will take inputs from each other. So this first cell will pass its input, that are we going from the left to the right, and the upper cell will pass its input from upside to the down, and this way we can ignore these at the edges because nobody is using them, but let me write it anyway. So imagine for a moment that I am passing the matrix A through the left and matrix B from the top. Basically what we need to do is, because I want to multiply A11 by B11, I will write down here the A11 and upside it will be B11. And because this little guy, this little cell will do multiplication, it will just multiply A11 and B11 and store it in its registers. And if there is a previous result, it will just accumulate the results. Let's now assume for a moment that there is no results and all of this is zero right here. So it is zero out, it is clear. For the first cycle, we will compute this A11, B11 and store it just right here. And furthermore, we will pass A11 to the right and pass B11 to the down. By passing A11 to the right, we can use it for computing C12. When we pass A11, we can just pass B12. However, we're gonna pass it at the second cycle. So for the first cycle, we will pass nothing to that cell. However, in the second cycle, we will pass the B12. And now you can imagine that when A11 arrives here, it will be multiplied by B12. And when it multiplies by B12, we partially solve the problem of finding the result of C12. And all of this can be formulated in a way that it is scalable. So even if I get all this hardware and just duplicate it like so, can duplicate it in a better way. If I get this hardware and duplicate it, you can see that now I'm solving a bigger problem. And now I can do all of this in a higher throughput. And even better, I will make it a square right here, like you can see. So this design is scalable. And this design preserves regular processing elements. And by utilizing this design, you can see here that we will have a huge arrays that will solve the Matmul operation. But what we need to make sure is these bubbles, these zeros are passed at the right time, so no input is dirty, or we solve the problem in the right way. Because imagine if there is no zero here, there is no bubble here, A21 will come too early and it wouldn't be multiplied by B21. So at the second cycle, these two guys will be multiplied and stored here. So we need to preserve this bubble. Unfortunately, these will have a specific pattern. As long as we preserve this pattern, we will be able to do matrix multiplication. So the question now here becomes is how are we going to use these small meshes to solve for much bigger matrices? And what I mean is, if our matrix multiplication results have the dimensions of 32 by 32 and I'm using this 4 by 4 mesh, how I'm gonna be able to do that? Now fortunately, because Matmul is a linear operation, we can just do divide and conquer. What I mean is we can divide the problem into solvable subproblems, then accumulate these results to just obtain the ultimate result that we are seeking. And you can imagine that we need to subdivide the matrices into tiles that we can compute, and we need to tile over the bigger matrix to obtain newer tiles and fortunately solve our problem. So let's take an example. Right here we will have 8 by 16, which is multiplied by 16 by 8 matrix, which will result in an 8 by 8 matrix. And we are going to use a very small mesh, which is going to be 2 by 2. We can imagine that by using that small mesh, we will be only able to solve this part of the problem. And what we can do is solve this part, then solve this, and solve that. And by iterating over the bigger matrix, we can subdivide it like you have seen here into subproblems that we can solve, and we can fortunately obtain our result. However, a bigger problem is Alright, I'm solving only this part of the matrix, but the other matrix is so huge. Like you can see, it is 8 by 16, and this is 16 by 8. How I'm gonna fit all of this into my registers? Wouldn't this be an overhead to uh, requesting this data from the memory over and over again? So to solve this problem also, what we're gonna do is we will gonna use SRAM banks, and we will store part of the matrix, part of the huge matrix in these SRAMs, and then retrieve what we want, retrieve what we need from the SRAMs. This way we can reduce the memory overhead, but also at the same time it is more expensive. However, it is much faster. So we need some kind of SRAM banks that will store part of the matrix. So as an example of caching, we can say that we are storing KT amount of data in our cache, and what that means is if KT is equal to 4, for example, what we are storing is up to here. So because we have a 2 by 2 mesh, we will store just this these rows, and up to 4 more columns is what we're going to store in the cache, and this will be our A cache. And the other side here, we can imagine that this is going to be our B cache, and we will retrieve the elements from here. So now, because we have stored a part of the bigger matrix in the SRAM, we can do a matrix multiplication on it and consume all that cache. Now imagine for a moment that we did this matrix multiplication and stored the result in a partial sum result called, like, for example, a partial C11, partial C1, and we will keep accumulating these partial sums to finally obtain this part of the bigger matrix. And we have computed the partial C1, we will compute the partial C2, and so on. You can imagine that we will need, what we need is four different computations, because we will tile this cache 4 times, one time for here, 1, 2, 3, and 4. If you do the math, so we need 4 distinct partial sums, partial C3 and partial C4, just like that, and this will give us the final C1. If we say this is the C1, this will give us the final C1. Now you can imagine that we need to tile our pointers, like B at the first computation phase, it will be here, then it will be just passed to here, then to here, and we will keep saving these new matrices to caches, and we will do the computation over and over again. After we have finished C1, we need to tile this pointer to here, and we will compute this time the C2, which I will color in green. So this is the C2, and we will do this over and over again until we finish the whole matrix. So after we have gained a rough idea on how are we going to solve this Matmul problem algorithmically, we can implement this algorithm onto the hardware and make sure that the Matmul functions correctly. You can see that MatmulController will access the mesh, and it will retrieve data from A and B SRAMs, send control signals to the shared mesh for computation, and then retrieve the results or even accumulate them. The MatmulController will also have access to the tile reader to retrieve from the main memory or the caches, the bigger caches, data related to A and B, or even the tile writer to finally give us the results. We can imagine also, if we take a closer look at how the MatmulController is using the mesh, that we need a BF16 to fixed converter that will either convert the input to BF16 from BF16 to fixed, or it will pass 0, the bubble like we have seen earlier. The reason we are using BF16 to fixed converters is to not deal with FPUs because they are so expensive and slow. This will cause in a minimal accuracy loss because we are going to use fixed point numbers that have high precisions. Also, we need for the algorithm to function correctly to store the tile m, tile n indices, base k and chunk k indices that are details of the algorithm itself, the tiling matmul algorithm. We need also to store the description that we are currently solving. And if we look at the signals that the MatmulController is receiving at the low level, it should run right now, which description it is operating on, and because we are always asking data from the DMA engine, it needs to receive this through its ports. So we are asking the DMA that we need to write the results, and after we receive that it is okay now to write your result, we will write it through this port, and we will ask the tile DMA engine, we need to read a couple of data from the main memory or other caches, will give us this data through this port, and after we have formatted these matrices, we can pass them to the mesh. So mesh A means meshes A input and meshes B input, and we will also pass the mesh accumulation input. So if the mesh needs to accumulate over any result, so it resumes from there. And finally, the mesh will give us the result that it have computed so far. Now, to make it easier for us to trace this hardware module and see how it performs in the wild, I have generated the waveform of this workload, which is called Atik smoke, which stands for Atik smoke test. We will run this basic matmul operation, and we will see how the signals are passing through the Atik controller to the matmul controller and to the mesh. Well, as you can see, because Atik controller should say to the matmul, now you should start the matmul, we are expecting it to output. If I open the scope here, we are expecting that the Atik controller, will tell the matmul to start at this specific nanosecond. And if we go to the code, you can see that the controller that we have been seeing here in the GTK wave is this controller, and it is just this Atik controller. And also we have a matmul module, this matmul module here, which is also in the GTK wave. It's just basically this matmul controller, and if I go to the matmul controller, I can see it takes an input from the Atik controller that it should start, and here we can verify that indeed we are starting the matmul operation, and this state waveform here tells us which state is the matmul controller at. So if I take a look at the finite state machine here, you can see that 0 is the idle. Then we init the tiles. What means to init the tile is to clear previous calculations. If I find it here, init tile, you can see we are zeroing out the A row and the accumulation, also the B row, the K base and chunk K. We are basically resetting all the options. Then after that, we are starting the A operations. What that means is we are going to load from the main memory, and we're going to load from the main memory to the SRAM that we have is load A. Then we're going to do the same thing for B. Then we're going to read from the SRAM to the registers, and we're going to latch this data, and then we're going to compute. So as you can see here, we have a very long state machine for just the matmul operations. Like you can see here, it starts from 0 and it ends up at 12. So we can just follow it and trace it. So I can see here that we are now at the second or at the third actually state. What third state is? It is start A, and after start A, I can see that the tile read command is ready. And when we are at start A, that means that we are sending signals to the DMA engine that I want to retrieve from the memory data about A. And at the third cycle, not the third cycle, but when we arrive to the fourth state, which is denoted by 3 here, we are just reading this data. And you can see that tile read out bits data is the data we are reading at that moment, And this right here is the tile read out bits last, tells us that now we have read all the data that we should read and we have stored them in the SRAM, and now we can proceed and actually fetch data for the B matrix. You can see here we also fetching data for the B matrix, and we finish fetching data for the B matrix at this nanosecond. After that, we are at the seventh state. And what does really seventh state mean? Let's see. So 1, 2, 3, 4, 5, 6, 7. We are reading the SRAM, and then we are going to latch these results for computation. You can see that we are doing it here. So IOMesh active means we are starting the Matmul, and tile write command means now we are ready to write the results to the output. So what I'm trying to say here is we have run the Matmul operations, then we are starting to write the results to the memory, and you can see here that writing is done and everything has finished successfully if you look at the logs. This is basically how the MatmulController is manipulating the data, retrieving data, sending data, and computing the Matmul operation using the mesh interface. We have talked in a great detail about what the MatmulController is controlling and how it controls. Now we can move to the attention controller. Now coming to attention, the real bottleneck here is not matrix multiplication anymore, because we figured out a way, an efficient way to reuse the data, to scale up our matrices, and just use bigger meshes to gain high throughput. However, the problem and bottleneck for attention is the softmax. The softmax needs to be calculated in an online manner, so we don't store the whole row in the accelerator itself, and we keep iterating in a fast way. And the implementation of this online softmax is not that easy on the hardware, because as you can see, we will always need to take exponentiation, and exponentiation needs a numeric way to be calculated, or you can have a lookup tables. And what lookup tables basically are, that you have a range of input values, and for this range of input values you have a range of exponential values. So you need to make sure that your inputs does not really exceed that range, or you have to normalize that range. And after that, we need to be also always multiplying and accumulating an exponentiated value. Now, why are we having all these problems is because softmax is not a linear operation. Like we cannot do divide and conquer like what we have done in the Matmul. So it is much more silicon, it is much more code, it is much more intimidating. However, if you look at the code here, we figured out I figured out a way to do it, and it is hard to digest first. However, if you think about this in more conceptual way, what we are doing is we having Matmul, and after that Matmul, we are dividing the results and normalizing them by the square root of the decay. And after that, we are taking a softmax. The square root of the decay is given by the user, and the kind of normalization, the division we are doing here is by just using lookup tables again. The softmax bottleneck is solved by this online softmax algorithm. Implementing it in the hardware is not that easy. However, it is a thing for you to check. Like I've said, it is normal Matmul. We are using this, not this. We are using this mesh again. We are saving these QK matrices in the SRAMs, of course, because we are going to multiply Q time by the transpose of K, and we are going to normalize using the lookup tables. As I've said, the big bottleneck in the attention controller is in calculating the softmax in an online way. However, other things are really much similar to the Matmul. We can now move to even other hardware modules, So as you can see here, we have now completed the command router, the Atik controller, the MatmulController, and the attention controller. We can now go to the description reader. And the description reader actually receives a start signal. And this start signal tells it when it is the right time to read the description from the memory. And it does that through the description address. So it gets the description address as an input, and it asks the DMA engine to give it the bits of this description. After it reads these bits, so this is read bit, it will store it and output the description. Now, what I mean by the DMA engine is, like you can see here, we have a DMA reader and we have also a DMA writer. This DMA is responsible of retrieving data, only retrieving data, because it is a DMA reader. What it receives is a command. This command is an output of the module that needs the data. So you can see here that description reader, because it needs some data, it actually outputs that command, and that command goes to this DMA reader, and the DMA reader asks this specific data from the memory. This kind of abstraction will make a lot of things clearer to understand the code, so that's why we did it here. Now, the DMA reader is responsible for retrieving the data actually. Other modules will only ask the DMA to retrieve the data, and the DMA will figure out a way using tiling to retrieve the data. Now you can see here that the output of the DMA reader is the DMA read bit, which actually is what we have asked the DMA reader for. Now moving to the next DMA engine, we can see it is the tile DMA. Now why we need a tile DMA? Because attention and Matmul, like what we have seen earlier, they operate on tiles, and we don't need a single byte. We need a huge tile, and we need to define this tile to a module that will actually take care of packing all this data and give it back to us. So this is what this tile DMA reader is doing. It receives a command. It receives a command from who? It receives a command from the MatmulController or the attention controller. You can see here that tile DMA read command. So this command goes to this tile DMA reader, and the tile DMA reader returns the tile elements, like what we have also seen in the waveform. Tile DMA reader also accesses the memory through tile link, like you have seen here. DMA read request. The DMA reader also uses the same protocol, which is DMA read request. However, the tile DMA is responsible for packing all this data to a tile that will actually consume in the attention or Matmul. The same thing for the tile DMA writer. Instead of reading, we are writing. Like you can imagine, we are now giving the tile that we want to write, and we have another command which is tile DMA write. And we need to tell the module that is asking us to write if we are done or not, if we are active or not. Now, to the tile link, we are sending the data with a mask. What the mask means is, imagine that we are sending 8 bytes at a time. However, our data is 5 bytes. We will mask the last 3 bytes until the tiling that these are not relevant. And the tile link will give us a response about if we have written the data successful or not. Now coming to these more simpler modules, you can see that we have a module that converts the fixed to BF16 and BF16 to fixed with a certain amount of precision loss. We also have a MAC mesh. A MAC mesh is multiply accumulate mesh, which actually contain a bunch of MAC cells like we have seen earlier. And finally, we have the tile SRAM. Tile SRAM is actually the cache, AB cache that we have talking about earlier. So when you stack a bunch of these tile SRAMs on top of each other, you can form a 2D array, and this 2D array actually will form the AB SRAM or the QK SRAM. And that's actually a general high-level idea about how these components are interacting with each other. What kind of inputs, control signals are they receiving and they sending? So now we have a great idea about how this hardware architecture will operate.